Special thanks to the International Raw Materials Observatory, a 2022 Earth Science Week global sponsor.
Thank you all for the kind invitation. My name is Federico Magalini, and I will try to discuss with you today in the next 10-15 minutes the science of keeping material in the loop. And I will start with some pictures that I took myself a couple of years ago. The first one I took in Ghana in the sadly known Agobloshi dump site, or as they call it, the recycling district of Accra. And it shows typical business day for guys trying to survive and trying to get, in this case, copper out of cables. And as you can see, it's easy to imagine the environmental impact of such practices, as well as the impact on the economy. And last but not least, the social reason or the societal reason why this is happening. Those guys are simply trying to get a couple of dollars out of this copper and trying to maintain their family. On the other side of the slide, you see a picture I took in Italy, as actually the neighbor of my uncle, and during the day the person is keeping a local collection point, municipal collection point for waste open, and then before closing is just handpick material waste reaching copper is bring in his backyard, where he's again trying to get copper out of the waste. And of course we have similar externalities when it comes to environmental impact, but it's pretty much different. The reason or the economic implication is definitely ignoring the legal framework existing in Italy, is hampering local businesses that is trying to collect and treat waste in a proper way, and ultimately simply trying to do this to cheat, to get an extra bonus at the end of the month. And of course, the leverages that we can use are different. In one case, you have awareness raising, technology transfer, capacity building. In the other case, we might have, yes, some awareness raising, but it's mainly about enforcement and prosecution. And I wanted to make this case or start with this example because sometimes we think that problems are far away, but quite often we have a similar impact even in our close network of people we know or companies we might interact with. The fascinating thing for me of the world of electronics is that we have a lot of different products. We can count more than 600-700 products type invented by engineers, by scientists. But when it comes to the end of life, they are usually collected and treated according to specific waste streams, 5 or 6 usually. And this is basically a need of depends on the type of technology that are needed to ensure proper collection and proper processing. You usually start collecting those products in waste streams, as I mentioned, and then they go through different steps, usually manual, semi-automatic, or fully automated processes, the so-called pre-processing phase, aiming at removing hazardous components or material, the depollution phase, and then creating or obtaining individual fractions, metals, non-metals, printed circuit boards, other fraction rich in specific component, which are then sent to downstream recyclers, and this is where the technology play a crucial role, and this is also where we have technology that are more material driven rather than product driven. We have of course here crucial role is played by technology when it comes to increasing the process efficiency, making sure the emissions are limited, making sure the yield is increased so that we can recover more material. It's interesting to consider there are always two different dimensions in waste processing. This is the case of electronic waste, but you can use this diagram for almost every type of waste. You have an horizontal dimension, which is explaining or bringing the environmental value to our attention. And then you have a vertical axis where you have the profit. So as you can see, you have 4 different spaces or areas in this matrix. And we start in the bottom left part of the matrix where you have activities or operations that are causing environmental damages and losses. And I hope that common sense prevent people to be and operate in this region. But sadly, we have people, operations company that try to exploit the economic value, the intrinsic economic value contained in the waste, damaging the environment. That's a typical example of burning cables, and this might be lack of technology, but might also be caused by conscious decision. That's why we put in this matrix the criminals, or we kind of identify this area or activities in this quadrant of the matrix with this nice icon or avatar. And then of course we have activities or operations that are having a positive environmental impact and profit. This is so-called market-driven solution. It's the best, if you like, best scenario that we can have. And there are material or particular waste streams that are really intrinsically in this area, so you can really exploit the economic value contained in the waste. You can do things according to best available technology and standard and still make money out of it. One good example is lead acid batteries. And then of course we have activities that are causing environmental benefits, but the economics are against the people that are carrying out such activities. So we said we call the saint. In this case, it's really important to have a proper financing mechanism which is ensuring operations can be sustained, because from a company perspective you need to be in the upper part of the matrix. From a policy maker perspective or from a societal perspective, we want to be in the right part of the matrix. So it's really important to set the proper rules, push for the adoption of best available technology, and make sure financials are in favor of entrepreneur of companies. Now there are interesting trends in the electronics sector, and I would like to use the mobile phone, which is quite an iconic product, as example to stimulate the debate later on, or to throw your attention to some elements. Mobile phones use a lot of network resources, a lot of fancy elements in the periodic table. This is because some engineers, some scientists identify the link between specific elements in the periodic table and functionalities, like in the case of indium, touchscreen, the case of ruthenium, to ensure there is more data that can be stored in the memory, in the memory stick or hard drive. And those metals are not usually primary metals that we are going to mine. Sometimes they are byproducts of mining of other base metals like copper or aluminium or lead or others, and we don't necessarily have all the material we want necessarily really available in case of need. Mobile phones are also an interesting product because they are pretty much used as example by policymakers, and we know that a lot of bad habit of people, like hibernations, are pretty much common when we think to mobile phones. And as you can see here, on the right part of the matrix, there are the results of a study we did a couple of years ago in France. We really carried out a mass balance of mobile phones industry in France, understanding the total amount of phones that are placed in the market. Those are being kept in the loop through reuse, repair, peer-to-peer exchange, those that are collected and recycled, exported. And as you can see, there is a quite substantial amount that is kept hibernated, and it's really important to understand that those patterns are really creating an impact, because every time we keep something stored in our drawer, we are also keeping stored and preventing resources, net resources, critical in some cases resources, to be reintroduced in the loops. And as you can see here in the chart, when you look at different markets, even different point in time, the patterns of consumers are really different. But hibernation, uncertainty, bad disposal, unsound environmentally, from an environmental perspective, practice are quite common. And it's really, in my opinion, underestimated the central role that consumers might play when it comes to end-of-life operations, because we might develop new technology, we might develop better processes, we might develop more efficient recovery processes, but if consumers are not doing the right action when discarding the mobile phone, or when not keeping mobile phones in the drawer, well, those efforts of scientists are a little bit dissipated. And I think one important element that I would like again to stress the attention or highlight is the fact that not necessarily, not always, we need to go through the entire process of collecting the material, collecting the product, recycling the product, going back to the material and reusing the material, because in some cases the critical elements are enabling certain functionalities, and those functionalities are implemented in specific components, and there is a better, even from an environmental perspective, case in keeping those components in the loop through repair, through refurbishment, working on modular products where components can be reused on different models, kept in inner circles for longer, because as you can see, the closer or the shorter is the loop, the better it is from an environmental perspective for sure, but also most of the cases from an economic perspective. And again, as you can see in this graph, in this chart, the role of consumer is really pivotal. So one of the main message that I would like to throw now on the table for the discussion is we are discussing today the role of science in keeping materials in the loop. I think it would be good to consider maybe a little bit more how we as user or modern technology can also play a crucial role, because as I said earlier, we can develop the best technologies to recover material, to process the waste, but if we don't have consumers making the right choice in the beginning, well, it's, I would say, a little bit harder to achieve our goal. I hope that those few thoughts will help to stimulate the debate. I'm definitely more than happy to interact with you live in the discussion with the other speakers as well. Thank you for your attention, and speak to you very soon.
A warm welcome also from my side to this webinar. My name is Luis Tercero. I work for the Fraunhofer Institute for Systems and Innovation Research in Germany, and I will be talking today about the promise and limits in urban mining, and especially what sets urban mining apart from conventional mining and what the similarities are. Urban mining depends on the anthroposphere. So everything that people make belongs to the anthroposphere, and the anthroposphere is of course a very large and very varied source of raw materials, or it can be if we use it that way. So the aim of urban mining is actually to manage and use these materials as a raw material supply source. So using the waste of today on the one hand, and on the other hand, anticipating and capturing the value contained in the waste of tomorrow. A lot of times we need to be prepared for scrap and waste types that are not there yet. For example, lithium-ion batteries, which we are introducing today and which will be becoming more and more relevant in the years to come. It's also important to remember um, that even though it's urban mining and we're talking about the anthroposphere, all metals and minerals in the anthroposphere came from conventional mining. So it's a longer chain to get to this mining activity from geological deposits over the anthropogenic stocks. But in the end, the source of all materials that we use, so firm they are not biological, is geological deposits that were exploited in the past or will be exploited in the future. Urban mining is an integral part of the circular economy. It is not the same as the circular economy. They do differ, and the circular economy is definitely a larger, wider concept. But urban mining is a very, very important part of it. When we talk about urban mining, we are talking about long-lived products and the recovery of the resources bound in those long-lived products. We are not talking about the recycling of manufacturing scrap. For example, very short term, we are not talking, so this is shown here. For example, things that go back from manufacturing to metallurgy and have a closed cycle. This is part of the circular economy, most definitely, but it is not considered part of urban mining. The same applies to activities like repair, reuse, and remanufacturing, where we keep things in the stock in use longer by enabling them to have longer service lives through a variety of measures. That would not be considered urban mining because we're not getting the raw materials back. We are saving resources, but we are not recovering the raw materials. Urban mining is more or less this last part of this cycle, and quantitatively it is dominated by the recycling of end-of-life scrap from both infrastructures and also consumer and businesses. Theoretically, this would also involve the recovery from landfills, which is not very widespread, and the recovery from mine tailings, which again, the urban mining grows every year in all of these reservoirs. And as we said before, from mining operations, we have a very large amount of tailings, but to date, these do not flow out in the form of significant amounts of new raw materials. So the deposit here is growing, but it's not relevant to material production for most raw materials. The same happens at the other end for the landfills. We have residues and not recycled end-of-life products that enter landfill every year that could theoretically be recovered. There are a number of projects that have shown for a wide variety of settings that it is technically feasible to recover those. So it would be possible to get raw materials back, but it doesn't work on the side of the economics. So today there's essentially no outflow on this, such that when we look at urban mining in the way it is there today, it is tantamount to the recycling of end-of-life scrap. And this end-of-life scrap comes from the stock in use. So we keep feeding our stock through new things that are built, that are sold, that are put into use, and after a service lifetime that depends on whatever that is, this material comes out in the outflow and becomes theoretically available for recycling. Since the inflow is generally larger than the outflow, we have an accumulation, and this stock keeps getting bigger and bigger every year for most raw materials. And the accumulation of the stock and the flows tend to be very regionally different. So we can look at this from a global perspective and take, say, a global stock of materials. Here I'm showing an example of copper for the year 2018. And the global picture is shown on the left, and it is shown to scale. So we have here the global picture containing buildings, infrastructure, industrial uses. We also have transport, which we tend to think about, but also consumer products, which are very, very close to us and which have a shorter lifetime. So they have a larger contribution to the stock outflow, to the scrap that we see. If you look at the distribution across the globe, we've split this into 5 separate regions. So we have North America, Latin America, the EU, China, and Japan. The rest of the world is implicit in the whole global picture. You can see that the size of the stock is different. If you compare, for example, Latin America to Europe, if you compare China to North America, you can see very quickly that the stock in China already in 2018 was larger than that in North America and that in the EU, which are similar, whereas the stock in Japan is about the same size as the stock in the whole of Latin America. However, the dynamics are different. So the stock in China, which is still building up a lot of its infrastructures, is first a lot larger. So it's more than the sum of the inflow to North America and the EU. And at the same time, the outflow is a lot smaller because the infrastructures, the buildings, the machinery, they are younger. They are not, there's not a large proportion of that reaching the end of life. It will be in the future. At this point, I would like to draw some further parallels and differences between urban mine and conventional mining. Like in conventional mining, there is a theoretical potential for the urban mine. This is everything that's contained in the anthroposphere. However, nobody's going to go and tear down a building just to get at the raw materials. So in practice, the production of the urban mine, unlike that of a conventional mine, is not something that you can change at will. You are limited by that which we are taking out of service and putting into the right channels for recycling. So not everything that's in use is actually available right now. There's a recoverable potential, which is the outflow of the stock, and from that recoverable potential, there's only a fraction of it which we actually capture, which doesn't end up directly in landfills or in some, well, be them legal or illegal, and which we are actually processing in such a way that the materials are captured. Not even if you put the products into a recycling stream, it doesn't mean that you will capture 100% of all raw materials. Of some, you will capture a lot. Of some, you probably not capture anything. And next to that, there is dissipation. We're talking about here chemical and mechanical losses throughout the lifetime of the products. There are things that are not collectible, and there are things for which we simply do not have the technology to recycle. Another peculiarity of the urban mine in comparison to the conventional mine is that the source of the material is distributed worldwide. And so there's a very, very long chain that ties things that we throw into the trash bin to recycled raw materials. And that chain can go wrong at a number of places. It first tries to accumulate all of those discards, separate them into appropriate qualities, and then dismantle, clean them up, sort them, and put them through appropriate processes. Sometimes this is material recovery, sometimes it's energy recovery, and sometimes it is simply landfill. One last thing I want to talk about today are recycling indicators, what they are and what they measure. So this is much like the recovery rate in a mine. And there are different kinds of recycling indicators that tell us different things. So one of them is, for example, how well is our collection working? Another one tells us how the separation is working. You put that together with metallurgy, you get at something that's called the processing rate. And if you put all of those together, you get at something that's called the end-of-life recycling rate. There's also there are also indicators that are based on metal production that measure independence from geological resources. And what I want you to take home from this slide is not necessarily all of the definitions, which we cannot really go into here, but that there is not the one collection rate. So when somebody, the one recycling rate. So when somebody says the recycling rate of this is this, there's a little alarm that should go off in your head that prompts you to ask, what are we actually talking about in this particular recycling rate? And with that thought, just let me close this presentation here and invite you to post your questions at the end of the session. I am really looking forward to the discussion. Thank you very much.
My name is Ola Isaksson. I'm very glad to be with you today, and I will talk about design for circular economy. I come from Chalmers University of Technology, and which is situated in Gothenburg, Sweden. We all know that we are on a non-sustainable track where the resource consumption is expected to increase over the years, unless we do something. Circular economy is one of such incentives, and we can see that one of the core principles of circular economy is that we should recognize the value of materials and extend that as long as possible through life. Now, if we see what happens around us, we, at least in Europe and probably anywhere, focus quite a lot about climate effects and decarbonization technologies. Electrification is one such, where lithium-ion batteries is, of course, a critical resource. And we know it's finite, and we also know that it's not geographically well distributed. So that means we get ourselves in a position where we rely on scarce resources. And on top of that, I'm not quite sure that we actually know all the consequences and effects of harvesting natural resources. So I'll talk about design, and design is really about finding, exploring, evaluating, defining, and validating solutions to needs. That's a fundamental approach in design. I'll show you how that can be helpful in also in a circular economy context. So if you look first into the incentives for a manufacturer to engage in circular economy and also develop solutions for circular economy, well, we can see that over the years the responsibility for products over its life cycle has increased or continue to increase by legislation. And we also see that the value by the customers or users is really transferred from the ownership of a product to what the product can do for you. That means we appreciate and we pay for use rather than pay for ownership. Lastly, we can also see that the value in materials, but also another type of technologies that manufacturers put into solutions and products, is rather high. Many companies are hesitant to relieve or leave their precious technologies in metals and resources for a second-hand market. So there are quite a lot of incentives really for manufacturers to go from a producer to actually a provider of solutions. There are many known and examples of this already. One interesting one, or a very clear one, where this change has been can easily be understood, is the Hawker Harrier. Hawker Harrier was designed and produced by British Aerospace in the 60s, and they had a classical repair strategy, and the customer paid to repair it. One of the components that tend to break every time was the canopy, It had a cracks, so you need to replace it, and it costed tens of thousands of dollars every time. Suddenly the British MOD wanted to change that, and they changed their business model. So they actually acquired or asked BAE Systems to provide uptime and availability of their aircraft. In no time, BAE Systems then redesigned the product. They removed the flaw, and suddenly the canopy was no longer a life-limited product. In this case, you can see also that that design, or redesign in this case, eliminated the waste of advanced materials. Now I'll talk a little bit deeper in design, although it will not be as extensive as you should need. But still, let's have a micro course in design. Can we think like a designer? The very first step, that's really to define the design problem. It's quite open that we see that any kind of problem that we would like to solve has multiple facets to it. There are conflicting needs, and we normally say that a design problem can be a wicked problem. Wicked problem means that you can't really satisfy all of the desires or needs at the same time, but you need to find a compromise. Now, it's very common that we actually solve the wrong problem. We don't really define the problem before we start seeking solutions. That means we improve something, and we have an idea about how the solution will be before we actually think and state formally what the problem is. So the designer always looks into the need and to try to work what is the need and what problems are associated to that need, and how can we then design and ultimately produce and provide a new product that solves that need. So a design principle is to say that a product or a solution that realizes a function. And a function is really what the product does, and that means you want to find what function really solves that need. Separating the function from solution is an abstract construct, but it's very useful because you can start identifying alternative solutions and look, how can I solve my functions? This is something we can do by separating functionality from solutions, and in this case we can have an example where if you want to control a direction of a vehicle, you can quite quickly imagine that you can do it in principally different ways, such as by mechanical means, as it has been done historically, or electromechanical solution, or potentially, as popular now, a more autonomous solution. These are principally different ways of solving the same function to control the vehicle. Now, you can actually start to model that. You can describe it as functional requirements and design solution, DSs. Doing that a little bit more elaborate, you can actually break down literally any problem or any function to how you solve that, and that will create a number of variants. That means you can start combining technologies, materials, solutions, or services, and start to understand how they relate to each other. So a new material, for instance, may fit into a system or a solution in another way than the existing ones. The point I want to make is if you work systematically like this, break things down, and systematically start seeking solutions on a sub-solution level, then you can actually start being innovative. So a design approach is really first to define the problem. Then we can, by, for instance, focusing on what the product does, the functions, we can seek alternative solutions, and of course later we need to evaluate whether those are feasible and if they have what value they provide, and validate they actually solve the problem from the beginning. Circular economy then, that sets focus on designable features for providing and ensuring sustained value over life. One of the popular models are the 9 R's or the 10 R's that all start with an R, that you can actually, the best one would be to refuse using a solution. That means a no solution or no product is probably the most viable one you can have, or you can eliminate redundancy in a system. The top ones are considered to be smart. That means you actually think a little bit differently, integrate functionality or increase the shared use of resources. Now, as we go below, we can also see that we can start remelting or recycling material, but normally that requires a lot of energy, and there are some side effects to that as well. But it's definitely better than putting them as landfill. What implications does it have then? Let's say the sharing part, which is enabled by us as consumers wanting to have something or accept the value of using rather than owning. So sharing, or in this case car sharing, is expected to have a large impact on the automotive industry. So that means if a portion of the community will accept car sharing or use car sharing and avoid traffic problems or parking problems in cities, as Deloitte actually has projected, then the sales of cars will reduce, but the usage per car will increase. This has a large implication also for the manufacturers, who need to start thinking about how they can sustain and repair and restore the cars, and the incentives again to increase ownership through life for manufacturers increases. Then if all of these are so smart, what's the trick then? Well, normally design solutions, or quite often circular economy solutions, are disruptive. That means that you can't do and realize these yourselves as a company, not even if you're a big company. You're dependent on your suppliers and customers, but often also authorities and infrastructure to move along. That means to succeed, you need to bring along all design influencers or stakeholders at the same time. That means we need to collectively act and move and transform. And as a designer, you need to be aware about this. So in summary, design for circular economy is really to understand the problem, systematically explore the alternative solutions, and bring in the R's. That means see the circular economy options as means that you can play with to find solutions. Then, of course, to succeed in practice, you really need to understand also and also manage the associated context. That means your supplier or your network for realizing these solutions. Thank you very much for me.
Great talks from our three speakers, Federico, Luis, and Ola. We will now move into our discussion session and get to as many questions as time allows. The first question I wanted to ask that I had in my notes is if any of you could comment on the importance of communication in your work and why community outreach and reaching to some of those stakeholders in that materials loop is important for the work you do.
I mean, I can start if you like. I think it's really important because more and more we are realizing, and the clients we are working with are realizing that it's not about one single company acting or finding a solution. It's more and more cooperation along the value chain. And I think if you look at the way metals are extracted, refined, used, disposed, recycled, there's a lot of different people, stakeholders, players, and so communicating what you're doing, engaging the other is really fundamental. No one can solve this problem acting alone.
I can follow on strengthening that even more. I think you're perfectly in line with what my comment, but also that means that all of us or all of you, if you have a career in this area, you're likely to benefit from thinking as a contributor to solutions or play along with those stakeholders and those networks. Hence, it's quite important to share a broad view of circular economy in this case.
I'd just like to add to that there's a bit of translation in that communication bit. So since we are talking about people from not only from different companies, but really from different backgrounds, be them technical backgrounds, cultural backgrounds, you need to also take a time to sort of translate your message so that it can be understood. So that's also a very important part of communication. I have nothing further to add to what they said already, because it's right. We need it. We need communication.
Yeah, perfect. A question I see in the chat. Oh, and this is actually one similar to I had in my notes too. For Federico, in reference to your graphic showing recycling, reuse, and storage of products by country, how does one measure the amount of these activities by country on a periodic basis to assess if there are changes over time? Would this be something initiated by government entities, regulation of retail and manufacturers to track this information, or another pathway?
Well, first of all, let me also add to before that tomorrow is the International E-Waste Day, which is a chance to have raise awareness about proper collection of e-waste all over the world, and there will be thousands of activities coordinated all over to again stress how important it is. Going back to this question, yes, I think usually the responsibility of tracking this information is usually lays with the government. In some cases, regulation like the European WEEE Directive or similar legislation popping up in other countries give the countries the role of track how much products are being placed on the market, how much products are being collected, recycled, if recycled, through which route. So that's crucial role. Having data is really important. Without data, you cannot even drive new policies. You can know where you are. You cannot plan investment in recycling infrastructure. Data is a key, and we need reliable sources for data. We have Eurostat in Europe. We have national government statistics, statistical office. So that's really key.
Perfect. Yeah, now I'm seeing a bunch of questions trickle in the chat. The next question I see is, are there specific materials that are particularly amenable to urban mining? What sorts of materials are people starting to focus on in Europe?
Well, if you look at the European Commission, we have since now more than 15 years a list of metals, critical raw materials, critical for the EU economy. So the European Commission is constantly updating this list of such metal. On this list, you have platinum group metals, you have rare earths, you have other metals that are key in application connected to decarbonization of the economy, connected to medicine, connected to IT infrastructure. We have such a list, and this list is constantly updated by the European Commission.
If I may add to that one, there's a bit of a difference about what we talk about a lot and what's really amenable to or really the basis for urban mining. So the list of critical raw materials is meant to focus the attention of politicians on issues that are there. At least that's what we were thinking about when we built that the first time around 2009, 2010, with the ad hoc working group on defining critical raw materials for the EU. And right now, as Federico just mentioned, there's it's in the works, the new list of critical raw materials. It would be the 5th edition of that. And if you look at those raw materials, they tend to be sort of the small raw materials. You will find platinum group metals where the world production is on the order of hundreds of tons. You won't find things like iron where you would have, a billion tons per year plus, or steel or aluminum with 60 million, or copper with its 20 million. And these, they are not disconnected. So if you look, for example, at the recycling of electronics, the value driver for that is mostly gold. If you take a phone and you realize what the material value of it is, it's like $1. And of that $1, most of it is gold. But you cannot recycle the gold on its own. You need to recycle the copper. If you're doing it in an industrial scale, you will throw that phone in a facility that recycles copper and recovers the gold and the nickel and the cobalt and so on and so forth. So you do need the base metals and their recycling in order to be able to recover also the minor metals from high-tech gadgets that we have in our homes today.
Perfect. The next question I'm seeing in the chat is, there is a lot of speaking about the mining and the use of raw materials and minerals, but not a lot about how the extraction of the materials affects the ecosystems from which they are taken off. Is this something that is considered when obtaining materials? And if it is, how are we making sure the ecosystems from which these materials are taken are not heavily impacted?
I think that there is an important element that this question is highlighting. The fact that we are sometimes looking at mining like the bad guys, it's heavy, impacting, and so on and so forth. But the reality is that if we look at the transition to greener, cleaner economy, decarbonization, actually we'll have to mine more metals, copper and other elements, because those metals are essential in this transition. Now, of course, we need to make extra effort, and we are involved, and we see this happening a lot in the mining sector in particular. We need to make an extra effort to decarbonize, for instance, mining operations, and that's quite a trend we see in that industry. But if we want to transition to new green decarbonized economy, we will need more metals. That's for sure.
Perfect.
There is also a contribution, if I may add to that one, there's also a contribution, a very strong one, from regulation. So how regulation is put in place and how it is enforced. And in the end, say, taking care of these ecosystems will cost us. This is what Federico was mentioned in his graph with the four quadrants, right? So it will diminish the profit. And it's a matter of whether companies that are taking proper care of the environment are also still able to be competitive. And there are a lot of examples in raw materials where we have seen a shift away from responsible technologies or higher environmental standards towards locations where the governments were willing to pay the environmental price or the social price of disregarding the environment. And think of things like magnesium, think of things like rare earths. Those are things that do not need to come mostly from China, where they do today. They could be coming from elsewhere in the world, and it's a matter of costs and willingness to pay or not pay that environmental cost.
Perfect. Go ahead.
And if I may comment very, very briefly as well, I agree that's a fact. That's where we are. But it's also a consequence of us exploiting resources that are limited in some sense as a global community, and we don't have a big father of the earth who could tell people what to do. But there is also the side that there are actually increasing awareness in communities about the value of being more sustainable. The market forces are starting to, at least in Europe, play for these arguments. That's also a factor that may be of interest.
Yeah, no, perfect. And then I'm seeing the next question is for you, Dr. Ola. Why do we need to think like a designer? Could you explain a little bit more in depth for separating function from solution, an abstract concept a bit?
Yeah, it's natural for designers, or if you're trained in design, where it's not it's a useful construct to begin with. The most easy example would be the quote from Henry Ford when he started mass production of cars. If we would have asked a taxi driver 120 years ago what they wanted, they would have asked that they needed a faster horse. That means you tend to continue in the way you see, or in your way forward. Now, if you train yourself as a designer, you start valuing the function and what the product does really. And then you can systematically start thinking or addressing that as a problem or an opportunity. Yes, it's more abstract, but it's also very concrete. Think of a smartphone. Nobody actually wanted a smartphone. And not even some of the brands such as Apple did really realize, I think, the value of this functionality they provided. They actually don't sell a phone really, although they charge a lot for it. They actually benefit quite a lot from the services that you can provide using the phone, the App Store in this case. The same goes for the other Samsung and others. Now, when we as consumers, we probably also are getting more used to seeing the cell phone as a platform, providing services. So that means we really appreciate the value of having access to a lot of services rather than owning the goods. So this is a long-term serving trend that reduces the focus on ownership to the favor of what utility the products provide. And that's a market shift really in thinking. And back to the design thinking, I think, as we said, it's a useful construct to think in this way, work systematically. And also when it comes to circular economy, it's a broad concept. It relies on collaboration and common understanding in disciplines that are not traditionally thinking as designers, like legislation or in suppliers or materials or whatever. I hope that made it a little bit more clear.
Yeah, no, perfect. Thanks for clarifying. The next question go ahead. Oh, go ahead. You can speak.
I just want to say something about thinking of a designer. I think it helps also to understand why things are the way they are. You know, designers are trying to meet most of those multiple dimensions, right, in these wicked problems. And if you're sitting at the end of that chain and looking at the products come out, you know, as a recycler, you're on the receiving end of trends such as we want to have lighter products, we want to have miniaturized products, therefore there is less material in them, therefore there's worth less, and then there is it's a lot more work for a lot less reward to recycle them, and that's a trend that comes from the consumers and from the technology development that will affect how that loop is brought together. And sometimes it's less, sometimes it's more, but there's a need for communication there between the very beginning of that circle and the very end of that circle. And so we're back to what the circular economy is, why design for the circular economy is important, and why we need to talk to each other along that chain.
Yeah, I think I would like to add an important element, the fact that we cannot expect the recycling process to be economic enough to pay off or to trigger the recovery of all the materials that we consider critical. And we know, because we have been working a lot on European funded projects as well, like sea waste, there is no business case to recover the elements that the Commission put on that list as a criticality. And designers are doing their best to reduce the amount even of precious metals that we put on products, cobalt in batteries, gold, platinum, palladium. And sometimes recyclers complaining because there is less and less value in the products we are recovering. But we should remember that the recovery materials, critical materials from waste, is not an economic issue, is a societal issue, is a matter of keeping resources in the loop. And that's a key important part. And sometimes, as I was mentioning in my presentation, you don't need necessarily to go back to the material stage. You can keep the resources in the loop through reuse of components. So you can be smarter even through design, working on modular products, keeping components in a longer loop to ensure resources are preserved.
So may I have one more example on that? Mm-hmm. I worked my entire life in aerospace and aero engines, where the prevailing strategy has been to improve performance, extend life, be more efficient for engines, lighter designs, etc. forever. That has resulted in the use of more advanced alloys, more sophisticated elements that are more difficult to reuse or treat or process, and more expensive. But there are signs of that being changed actually. So it's easy to think that, okay, circular economy means that you should extend that further. But that would result probably in even more obscure or expensive solutions. There are signs that you should actually make them less long-living, but more simple to reuse and very much lower cost. So there are new business models coming up really, where it also get a shorter life cycle for the manufacturers to actually be part of the post-manufacturing ownership as well. I don't say it's there fully, but it's there are signs there.
Perfect. The next question I see in the chat, in reference to the recycling of materials that have potential use in the steel sector, is there any technique that is currently being utilized for this recycling of steel?
Yeah, recycling of steel it's a huge business, but it has let's see, electrochemically it has its troubles, right? So it's very easy for steel to oxidize. So if you have a mix of iron with other elements, then the very last thing you can recover is the iron. So if you have things like, say, copper, which is relatively what do you call? It's relatively hard to oxidize, and you can separate that. You can separate things out. If you're recovering steel, you're kind of stuck with what you get in the feed. So you can only mix the steels. That's what there's a lot of manual sorting in steel. So you will sort out things like stainless steel from buildings and special steels because you can only remelt them and then add a little bit of this and a little bit of that to recover the properties of the entire material. Things like copper, things like cobalt, like lead, you can refine all the way to the actual metal and then remix it any way you want. So for steel, the key thing is sorting, pre-sorting at the beginning, being able to differentiate between different kinds so you can do the right remelting.
Oh, perfect. And then another question I had in my notes is the materials and the research, the field of work you guys are looking at, everything you're diving into and kind of, emphasizing this, keeping materials in the loop. What are your plans like moving forward, your like future outlook onto like, do you want to make these resources something that you can share with the public and maybe incorporate in some like educational components for universities or people to utilize to kind of teach these topics to the public, because this is kind of a sector of geoscience that not many people are aware about, that it like relates to the economy, although it's very prevalent in their everyday lives with their consumer choices and all the technology they're consuming. So I'm curious, what are your plans moving forward with the research and the findings you guys kind of have on the broader picture of this?
Well, on the education part, I think there are initiatives every now and then. So, some years ago, we gave a seminar for high school teachers to teach them about critical raw materials and see whether they would take it into their schools. That was a regional initiative here in Germany, but I don't know actually what became of it anymore. There is the European Institute of Innovation and Technology. There's a section on raw materials, and they fund a lot of projects on education at the master's level, the PhD level, also for professionals, lifelong learning. So just 2 years ago, I had a project actually with Chalmers University designing a course on critical raw materials. What are critical raw materials? What do professionals need to know about it? What do PhD students in material science or in geology need to know about this, so they can take that a little bit with them. We also have some projects that make resource efficiency materials for grade schools, actually trying to get just smaller children's grade and middle schools to start thinking about that, because they actually are very interested in it, and they just sometimes need the stuff that they can work themselves on.
Perfect. That's about all we have time for today. If you have any questions that were not addressed today, you can email us at webinars@americangeosciences.org, and we'll make sure to send those questions along to the speakers. Thanks again to the International Raw Materials Observatory for sponsoring this webinar. And I also want to give another thanks to our speakers, Federico, Luis, and Ola. Take care, everybody.